But that's okay, because if you did it once, it's going to be the same forever, because it's the same structures. But the concentration term is going to change. Did you do this in a cell where there's 1 millimolar glucose? Or did you do it in a test tube where there's 1 molar glucose? Concentration can differ. And so that's going to be, to go back to math, our independent variable, the thing we change. And if we rewrite that the way a biochemist does, we derive the bottom equation here, which is actually right here. We just compressed some terms, which is the idea that our delta G is going to be some value that we look up. And the way we kind of indicate to ourselves it's something you look up in a book or look on the internet for is this 0 or not, which means standard. It's not something you're figuring out yourself. It's some standard value. And so we talk a lot about this idea of a delta G not, and that not sign means that this is a standard value. You look it up in a book. It's something you look up. It's a standard value. And we need to define what that standard value is for it to be meaningful, so that when you do something with it, you can do it. I'm going to skip the second part. We're still talking about the first part again to get here. And summarize. Don't worry, we're going to get here too. Don't freak out. My slides are bad, and I should feel bad. We'll have this first term, which ultimately is the structural differences. There's bonding and structure differences between products and reactants, which we just look up. And I don't know why. There it is. I'm sorry, it was like 3 slides in. My apologies. Here's what we mean by standard, right? We put that little 0, that standard sign right here. Here's what we mean. We mean 298 degrees Kelvin. We said it was going to be a constant temperature. Bond strength depends on temperature. If you make things hot enough, bonds break, right? So we need to define this. That standard sign means we're at 298 Kelvin. And we need to know something about the reaction we're measuring. So we define this as the concentrations of everything. The concentrations of everything are 1 molar. And we're at 1 atmosphere of pressure. We said we need a constant pressure, 1 atmosphere. But this is a problem. If we say that we define the concentration of everything to be 1 molar, which is what we typically mean when we write this. If you were in physical chemistry and wrote this, everything's 1 molar. But in a biochemical context, that would mean protons are 1 molar. Right? Everything's 1 molar. What's the pH of 1 molar protons? pH equals negative log of concentration of hydrogen. pH equals 0. That's incredibly acidic. I can tell you how any biochemical reaction reacts at that. It falls apart. Yeah.
But wouldn't you also have 1 molar or base?
Yeah,
too?
you would. Yeah,
So
it's
would
problematic.
that-
Yeah.
Okay.
But yeah, it leads to some weird situations, right? So biochemists said, you know what, let's get out all this. Let's put this little thing here, which we call a prime. Our little, apostrophe, which we'll call prime, which means let's amend this 1 molar everything. Let's put a little asterisk there and say, except the concentration of protons is 1 times 10 to the negative 7th. That is, it's pH 7. And the concentration of water is water. If we only had 1 molar water, we don't have much water around. The natural concentration of water is about 55.5 molar. So if we assume we're in liquid water that's behaving normally, we can't assume 1 molar water. That wouldn't work. So this prime tells us, hey, we're in a biochemical state. Let's put some reality. Let's fix this thing. And so this is what essentially a whole generation of grad students had to do. They got a test tube, and they made sure it was at pH 7 in water, and they put in 1 molar of glucose, and 1 molar of oxygen, and 1 molar of CO2, and 1 molar of water, well, we already have the water assumption, let it proceed to completion, and measure that value for us. Give us that structural value, empirically derived. Give us that delta G not prime. And literally, you can go on the internet or get an old school book, and there are factually tens of thousands of these pre-calculated that you can just look up and use. Every one of those experiments probably took a grad student at least a week to like get the kinks worked out, measure good data. You pick up one of those books and it's like hundreds of people's careers worth of time. It's kind of humbling, right? But the benefit of that is you can just look it up. Very rarely can you not just look up that value. Yay, that's good. But now we want to turn, my slides are bad and I should feel bad, this weird entropy term, how do I measure entropy, into something useful. And we want to turn it into a concentration term. And to do that, it turns out that we need to normalize it a little bit. To get from entropy to concentration, we have to throw in the universal gas constant, which has to do about collisional frequency, which really relates to concentration. If you have two things very crowded, they're going to collide a lot. If you have two things very spread out, they're going to miss each other a lot. They're not going to collide very often. So the universal gas constant, which has to do with collision frequencies and rates and all that stuff, we'll throw in. And that allows us to turn this vague entropy term into what is the factual measurable concentration of your products versus the factual measurable concentration of your reactants. It's all in molar. It's all stuff we can work with and measure physically. Life is good. And that gives us the ability then to really predict reactions by looking up some standard state and saying, but you know, I didn't do it with 1 molar stuff. I did it with X and Y concentrations. Is that still going to be spontaneous? Is that going to work? Is it not going to work? We can predict all this. And that gives us our main equation, which has now been written up there for a while, but I'm going to rewrite it big and again to talk about it. That our delta G will equal our delta G naught prime plus the universal gas constant times temperature times the natural log of concentration of products over the concentration of reactants. And that equation is going to be incredibly powerful and useful, and we're going to get a lot out of it. With me so far? By the way, on this slide as a reminder, if Gen Chem's been a long time ago, that if you have A coefficient molecules of A, so in our example, 1 glucose and 6 oxygen, even though you're adding them in the equation, in the math here, you multiply them, and you raise to the power of their coefficient. So it'd be concentration of glucose to the 1, because there's 1 glucose, times concentration of oxygen to the 6th, because there's 6 oxygens. So just a reminder, if it's been a while, converting from equation to one of these coefficients, how to do that. We'll do it a lot together. Don't worry if that's like gibberish to you right now. Good stuff. We're all on the train. No one's fallen off. No derailments. Okay. Here's why I think Hosea Gibbs, when I write it this way, it becomes really apparent to me that he's pretty damn awesome. On this side, I have a dead marker. On this side of the equation, I have energy, right? This is my energy. Is it favorable? Is it not? It's a measure of energy. And on this side, I have concentrations of stuff, which has to do, and this thing about how much they collide. Temperature is a measure of motion, right, at the molecular level. It's a measure of how fast things are moving. So I've got some kind of speed here, and I've got concentration of things and how they're arranged. some kind of mass, some kind of stuff. In the 1870s, Hosea Gibbs said energy is related to physical mass times the speed of that mass, related to that speed of that mass. Einstein thought of this in the 50s? 40s? 30s? My history just got bad. Whatever, 60 years later, and we honor him for this amazing insight, when Hosea Gibbs in his shack thought of essentially the same concept 60 years earlier. He said energy can be expressed as things of how fast are things moving around and colliding with each other, and what is their mass like. That's pretty cool to me. And I'm not trying to say these equations tell us the same thing about the universe, but they do have this eerie similarity in reminding us that energy is related to mass and speed of things, which is pretty crazy to me, honestly. And I would be remiss if I didn't write the actual equation, because Einstein's actual equation takes into account momentum as well, but we tend to simplify it a lot and pretend things are at an absolute reference frame of zero motion, which doesn't work. All right, so this is the equation we have. That's all grandiose and fun. Let me put it into useful terms. Delta G is going to be our actual energy, like what you'd find in a cell. Delta G naught prime is going to be our standard energy that you'd look up or perform in a test tube. R is just the universal gas constant. It's a constant. T is just a constant. It's a temperature, and we already defined we're at a standard fixed temperature. Ln is just a natural log transform, and this is just concentrations of stuff. What that means is I can interconvert both ways. This I can just look up, so I'm just going to take that as a given. If I want to know the actual energy inside a cell, is this happening? Is this spontaneous? All I need is the concentrations of stuff. Put in the concentrations. I looked that up online. I looked that up online because I can never remember it. Looked that up online. Looked that up online. Boom, energy. Or conversely, if I can get a bead on the energy, is this spontaneous? I can figure out the concentrations. And I think that going that way is the cooler one. If you tell me, hey, in the liver it's spontaneous to break down caffeine, I can estimate how much caffeine there must be in the liver. If you tell me about the energy of a system, I can tell you the concentrations of the things in that system. And that, to me, that direction is the crazy one to go. Because that doesn't seem right, right? You're just like, oh yeah, it's spontaneous. And then like I can do a little back of the envelope math and be like, here's the concentrations. Booyah, mic drop, right? Whatever. So we're going to be using this equation a lot. Because it gets tiring to write out products over reactants over and over, we usually abbreviate that as Q for the quotient. I don't know. QU2, I don't know. It's a Q. So we get that equation, delta G equals delta G naught prime plus RT ln of Q. Good stuff? Yeah.
Can you use a K as well? Because in like KSPs.
Yep, not yet, and I'll show you why. We are currently assuming that what we're trying to get at is the real life energy, what's happening, right? Another way to put that is what's happening when you're far from equilibrium. But what if we are at equilibrium? And that's a useful thing here. Oh, slide, there we go. Notice that if we are at equilibrium, the reaction is done. The reaction is complete. Equilibrium means our delta G is 0. That's the definition of equilibrium. The reaction's driving force, the actual energy is done. That's what equilibrium means. If our delta G equals 0, by convention, we then call it a KEQ, K equilibrium. Because those concentrations are going to be at that equilibrium finished state, and they're going to be a constant. But in the actual cell, they're not a constant. They're probably changing all the time. So that's where we get that in. And that gives us a useful reformulation, which I'm going to do on this board, because I want to keep it up. Again, if our delta G equals delta G naught prime plus RT ln Q, and we assume equilibrium. At equilibrium, the driving force of the reaction is 0. That's what equilibrium by definition means. So 0 equals delta G naught prime plus RT ln Q. I'm going to subtract terms, and I get negative RT ln Q equals delta G naught prime. Subtracted RT ln Q from both sides. That looks kind of weird, so we just flip it for funsies. And we get delta G naught prime equals negative RT ln. And since this is going to be a constant now, we just call Q KEQ. But it's functionally the same thing. And so we get this formulation, which tells us nothing about what's actually occurring, because we already said what's actually occurring is nothing. We said we're at equilibrium, 0. But it gives us a really shorthand to compare. If we can look up that standard value, what does that tell us about how much product and reactant we'll have at equilibrium? Will it have more product and reactant or less, or whatever? More product or more reactant? So it's a useful conversion factor. Again, converting energy into mass or mass into energy. And that's fun. To me, it's fun. So let's put something to this. Why do we care? What does this do for us? I have a whole bunch of reasons to show you. If my slides will work. Oh my God, come on, slides. But they won't. Okay, no, there we go. So here's the kind of thing where this intuition becomes useful and powerful. Let's say I'm looking at this process. And just as a warning, right now I'm talking equilibrium. We're going to get to real life in a second, but I'm going to start us in this simple case. So if you're like, where am I? We're looking at this equation right now. If I look up and I find out that L-malate, this is an intermediate of the citric acid cycle. So when you eat a cheeseburger, it eventually ends up in your mitochondria, and the citric acid cycle kicks in. We're going to learn all about it soon. L-malate reacts with an intermediate called NAD+, nicotinamide adenine dinucleotide positive, to form a new chemical, oxaloacetate. It's another intermediate of the citric acid cycle. It's a really important one. And NADH and a proton. And that this reaction has a delta G naught prime of positive 29.7 kilojoules per mole. Already, the positive sign should tell you whether this is spontaneous or non-spontaneous. Non-spontaneous. Another way of saying that is non-favorable. Favorable and spontaneous are very closely aligned. So that's fine. It's not favorable. But how not favorable? If I opened up the cell and I measured how much malic acid I have versus how much oxaloacetate I have, well, okay, it's unfavorable, so which one would I have more of? Malate. Reactants will be favored, right? It's not going to move forward. It's unfavorable. So I'm going to have a lot of this, very little of that. But how much? Right? Notice you don't need your calculator right now. I think I saw one or two people's eyes going, oh, you're right. You don't. Again, when I ask how much malate compared to how much oxaloacetate, and we know it's unfavorable, so malate's going to be favored. Here's our MCAT test taking strategy. Don't bring out your calculator. Bring out your dead. What's the only situation where I have more malate? B. I don't need math. I know there's got to be more malate because it's unfavorable. There's only one answer where there's more malate.